Imagine for a moment that you are drifting in the silent, velvet dark of the cosmos. You are far from the noise of cities, far from the weight of gravity, far from the daily rhythm of human life. You look back toward the center of our solar system, and there it is, the sun. For thousands of years, our ancestors watched it rise and set. They built calendars around it, worshipped it, measured survival by its light. We called it a constant. We called it steady. We called it quiet. Even in the early textbooks of space science, astronomers wrote about the quiet sun, as if it were a predictable engine, a reliable furnace burning in the dark. But the more we have looked, the more we've realized that our star is anything but quiet. It is a raging, churning, astrophysical laboratory, a sphere of superheated plasma woven through with invisible magnetic fields, constantly shifting, erupting, and breathing. And right now, something unusual is happening on its surface. There is a hole in the sun, not a crater, not a missing piece of rock.
A vast, dark void has opened in the solar corona, the sun's outer atmosphere. And what is pouring out of it is a relentless stream of charged particles, traveling at millions of miles per hour, crossing 93 million miles of empty space, heading straight for our tiny blue marble. To understand why this is happening and what it means for us, we have to step back from the present moment and look at how we first began to see the sun for what it truly is. We have to go back to the pioneers who first lifted their eyes above the veil of Earth's atmosphere. Before the age of modern satellites, before supercomputers and real-time space weather forecasts, there was Skylab, America's first manned space station, launched in 1973. A fragile orbital laboratory built from modified Apollo hardware, carrying 3 astronauts who would change how humanity understands our star. Gerald Carr, William Pogue, and solar physicist Ed Gibson spent 84 days in orbit, manning a dedicated solar observatory bolted to the side of the station. It was called the Apollo Telescope Mount, and it was equipped with instruments that could finally block out the blinding disk of the photosphere and peer into the ethereal, glowing crown that surrounds it, the corona. What they discovered in those months of observation shattered centuries of assumptions. They saw that the sun was not a static ball of light. It was alive with magnetic loops, with explosive flares, with vast rivers of plasma arching outward and collapsing back onto the surface. And they saw something else. Dark regions. Areas that appeared empty, cold, and hollow in X-ray and ultraviolet imagery. They called them coronal holes. They did not know it at the time, but they were looking at the birthplaces of high-speed solar wind. They were watching the invisible breath of our star escape into the void. These are coronal holes, and through them, solar particles escape at incredible speeds. They appear dark in extreme ultraviolet imagery, not because they are empty, but because they are less dense and cooler than the surrounding corona. The plasma flows outward so rapidly that it does not linger to emit bright radiation. To our instruments, it looks like a void, a hole, but it is actually a highway, a cosmic fire hose aimed into the dark. These holes can persist for weeks, sometimes months. They rotate with the sun, reappearing every 27 days like a celestial metronome. And when they rotate into alignment with Earth, they unleash high-speed solar wind streams, not as violent as coronal mass ejections, not as sudden, but far more persistent. Speeds of 500 to 800 kilometers per second, millions of tons of charged particles, streaming past Mercury, past Venus, past our moon, and heading straight for us. When that wind reaches Earth, it does not strike us directly. We are protected, wrapped in an invisible shield generated by the churning iron-nickel core deep beneath our feet, the magnetosphere. It stretches tens of thousands of kilometers into space, forming a teardrop-shaped bubble that deflects, channels, and absorbs the relentless stream of charged particles. Without it, Earth would look like Mars, stripped of atmosphere, barren, lifeless.
But the magnetosphere is not a wall. It is a dynamic system. And when the solar wind is strong enough, it bends. When high-speed streams from a coronal hole collide with Earth's magnetic field, they trigger a geomagnetic storm. Not always violent, not always dangerous, but always real. Particles are accelerated along magnetic field lines, funneled toward the polar regions, where they plunge into the upper atmosphere. They collide with oxygen and nitrogen atoms.
They release light, green, red, purple, dancing across the sky. The aurora, a beautiful byproduct of an invisible collision. But beauty is only half the story. Geomagnetic storms induce electrical currents in the Earth's crust. Long conductors, power lines, pipelines, undersea communication cables. These currents can overload transformers, fry satellite electronics, disrupt GPS signals, ground aviation over polar routes. In March of 1989, a solar storm plunged the province of Quebec into darkness for 9 hours. 6 million people. No warning, no backup. In 2003, the Halloween storms damaged satellites, forced flight diversions, and caused power fluctuations across Europe and North America. And these were moderate events. What happens when the wind is stronger? When the magnetic field embedded in the solar wind points south, aligning perfectly to breach Earth's defenses? When the storm hits during peak solar activity? The most famous solar storm in human history occurred before we even understood electricity. On the 1st of September, 1859, British astronomer Richard Carrington was sketching sunspots through his telescope when he witnessed a sudden, blinding flash of white light erupting from the solar surface. He had no idea what he was seeing. 18 hours later, telegraph systems across the world sparked, caught fire, and continued transmitting messages on their own, powered by induced currents in the atmosphere. Auroras lit up the sky as far south as Cuba. People read newspapers by midnight light. We now call it the Carrington event, a direct hit, a coronal mass ejection of The Parker Solar Probe has flown closer to the sun than any human-made object in history. It has dipped into the corona itself, measuring the birth of the solar wind, understanding how coronal holes accelerate particles, tasting the plasma that shapes our world. Solar Orbiter is capturing the first images of the sun's poles, where magnetic fields behave differently, where holes may form and evolve. We are building a new generation of warning satellites, Lagrange point observatories, AI-driven prediction models, global response protocols. We are no longer waiting for the storm. We are preparing for it. The terrifying truth is not that the sun will destroy us. The terrifying truth is that we finally know it can, and that knowledge is our shield. We once called it quiet. We were wrong. The sun is not silent. It is singing. In magnetic fields, in plasma streams, in light we cannot see. The hole in the sun is not a threat. It is an invitation to look closer, to measure deeper, to understand the star that gave us life. We are small, but we are not blind. And as long as we keep watching, as long as we keep learning, as long as we keep building systems that bend but do not break, we will keep surviving. The cosmos is not gentle, but it is predictable. And in that predictability, we find our place. Not as masters of the sky, not as conquerors of space, but as students of a star that has been burning long before us and will continue to burn long after. We are drifting in the silent velvet dark, but we are no longer drifting alone. We are watching, we are listening, and we are ready.